Welcome students. In today's class we are going to learn about force directed scheduling. So, this is one of the heuristic scheduling. So, as we have learned in the previous classes that in scheduling problem is in general a NP complete problem. So, we usually go for heuristic based solution where we have a option to prioritize the operations. Right. So there will be priority among the operations, and based on the priority we are going to select operations in a particular time stamp, right. So, and also we have discussed that least scheduling algorithm in the previous classes, where we have one such priority we have understand, which is basically distance of the node from the sync node, right. So, and the distance is in generic graph when there is maybe multiple paths, I am going to consider the distance of the longest path, right. And we have seen that we can have both MLRC and MRLC problem formulation using list based scheduling, right. So, in going in that directions, now we are going to think about another heuristic based solution, is called force directed scheduling. Here in the priority function is different, which is basically a force. Okay. So, that we are going to learn today, but this was proposed by Pauline and Knight maybe 20 years back, and both this mean latency and this MLRC and MRLC can be formulated using this heuristic, which is force, right. So, let us try to understand what is force. So, it is a basically mechanical analogy that you have a say elastic spring and you try to spread it, right. So, you try to extend it. So, once you extend it, what is the total force is generated? It is the displacement of this two endpoints, whatever the displacement happen into some elastic constant, right. That is what is the overall force. So, basically in this particular work they try to analyze try to correlate the scheduling problem with this force this elastic force, right. So, let us try to understand how we can correlate little bit. Now, we will discuss these things in subsequent part, but let us try to understand. So, as we mentioned that what is the problem for us? We have given operations and we are just considering whether I am going to schedule this operation Vi in time step L or not, right. So, that is the decision I am making. So, so now think about this. So, what is going to happen that if I am going to schedule this operation Vi at time step L, so what is going to happen? So, it will increase some kind of concurrency in that particular time stamp, right, because if this particular operation is type K, so that I need at least one more of resource in that particular time step L, right. So, it is basically increase the concurrency in time step L. So, that something is you can think about the concurrency is the force in this context. So, it is actually increasing the force. It is not only that, you basically, since this operation could have been scheduled within some time frame, right, that we are going to, we know that this is basically TLP versus TALAP to TASAP. So, that is the range where this operation is schedulable, and if you schedule in a particular time stamp in that range, the other part it is not going to schedule, right. So, that means the concurrency is reduced for those state. It is not only that, you think about that now you basically schedule this operation in terms of L, and it has some subsequent operation, it has some predecessor operations, right. Now, the kind of operations the predecessor and successor operations, their schedulability also might be impacted, right, because for example, say one operation if you schedule in time stamp L, and this time the next successor operation could have been also scheduled in time stamp L, because this operation could have been scheduled if it is the previous operation is scheduled in L minus 1, right. So, now since I have scheduled this operation in time step L, I actually have an impact on the next operation, that now this operation cannot be scheduled in time L, it has to be scheduled in time step L plus 1. So, it is concurrency for time step L is also get impacted, right. So, these are the kind of force it can generate once you schedule operations in a time stamp, right. And if we just calculate this force formally mathematically, and I can actually utilize this force during my scheduling. Okay. So, that something is important, right. So, let us try to understand how to calculate this force, and then we will see how I can utilize this force in developing both MLRC and MRLC algorithms. Okay. So, let us move on. First we will understand the operation interval, which is already we are aware of, that we know that given a latency bound lambda, I know the ASAP tells me the earliest possible time where the operation can be scheduled, and the ALAP, which is as late as possible scheduling algorithm, will tell us that what is the latest possible timestamp where this operation can schedule. And if I say this the gap is mu for the operation I mu I, so mu I is for operation Vi, then so the mobility is basically mu I plus 1. Okay. So, why? Because say one operation can schedule it 1 or 2. So, its ALAP is 1, sorry, ASAP is timestamp 1, ALAP is 2. So, the difference is 2 minus 1 is 1, but its mobility is 2, right. So, that 2 minus 1 plus 1. So, that is why this is mu I plus 1, right. So, let us take this example. The ASAP solution is this, we all know that. So, this is the ASAP schedule, this is the earliest possible timestamp. Now, you think about the ALAP schedule, right. So, let me just try to assume that all operations are single cycle and the lambda is 4, right, the given time is 4. So, for ALAP I am going to put the ALAP quickly, which we already know. So, this is this 5, 9 and 11 can schedule here, 4, 8 and 10 will schedule here, right. So, this is 4 and then this 4, 8 and 10 can schedule here, and then sorry, this 4, 7 also, right. So, 7 can also schedule here. So, this can schedule here, and then 3 and 6 is scheduled here ALAP, and 1 and 2 is scheduled here, right. This is the ALAP schedule, right, and this is ASAP. So, we can find out the mobility of for each operations, which is basically we can actually identify from the scheduling time TS to TL, which is the TS is the ASAP time and TL is the ALAP time, and if I just put I here, this is for Vi. Okay. So, what is the mobility for this mobility plus 1, the operation interval for operation 1, it is basically 1, because it is scheduled in the same timestamp. For this also 1, 3 is 1, 4 is 1, this also 1, because it can only schedule in one timestamp. Okay. So, for this it can schedule here 2 and it is 4 here. So, 4 minus 2, so it is 3, right, 4 minus 2 is 2 plus 1. So, this is also 3, this is also 3, this is also 3, because it is 1, 2, 3, 3 minus 1 is 2 plus 1, and this is 2, this is 2, right. This is what is the operation interval for these nodes. Okay. Now, try to understand that operation probability. So, let us try to understand this term, which is called Pi of L. So, that means this is for operation Vi at time step L. So, basically the probability of scheduling operation Vi at timestamp L, right. So, that something is given by PIL. Okay, very important to understand this term notation. So, now you think about this operation say 11, right. So, 11 can schedule in timestamp 2 and it can schedule in timestamp 11, 3 and it can schedule in timestamp 4 also, right, because it in ASAP it is scheduled in timestamp 2, ALAP it is scheduled in timestamp 4. So, there is a possibility that this is the operation interval and it can schedule in any timestamp. So, what is the probability of scheduling in timestamp 2? It is 1 by 3, right. So, which is basically 0.33. So, that means P11 operation 11 in timestamp 2 equal to 0.33. Similarly, probability of operation 11 in timestamp 3 also 0.33, right. Operation 11 in timestamp 3, sorry, timestamp 4 again it is 0.33 and it cannot schedule in timestamp 1. So, probability of operation 11 in timestamp 1 is 0. So, this is how I can identify the probability of each operation in each timestamp. Basically, in the range TS to TL, in that range it will be 1 by mu I plus 1, right. This is what I have done here, and other cases it is 0, right. So, this is how I can do it, right. So, for each operation, each timestamp I can find out the probability value. Understood? So, this something is clear. Now, if I just do this operation type distribution, so now say I have different type of operator, and say this says that Q K L, that means it is for operator type K at timestamp L, right. So this QLK is saying that I already identified that what is the probability of each operation in each timestamp. Now, some of them operation is multiplier and some of the operation is ALU type, right. So, it can have different type as well. So, now I can actually sum up all the probability of that operation type K in timestamp L, then that will give me the QLK, right. So, for example, say I am trying to find out the for timestamp 1, okay. So, and for operator types a multiplier which is say 1. So, Q1 in timestamp 1. So, what is the probability of operation 1 going to happen here, because this is only can happen in timestamp 1, that we have already understand. So, this is 1. So, basically it is probability of operation 1 in timestamp 1 plus probability of operation 2 in timestamp 1, because I have to take all the multiplier type operation, right. So, then probability of operation 6 in multiplier 1, then probability of 8 in timestamp 1. I should write for all multipliers. So, there are 2 more multipliers are there, probability of 3 in timestamp 1 and probability of operation 3 in timestamp 1, right. Out of that 3 cannot schedule in timestamp 1, 7 cannot schedule in timestamp 1. So, this is 0 and this is 0, right. So, I can write that. So, P1 is 1, P21 is 1, because this operation can only schedule in timestamp. There is no probability it can schedule in other timestamp, because the ASAP and ALAP timestamp is same. So, that is there is no kind of mobility for this operation, that we have already discussed many times, right. So, now this is 1, this is 1. So, this P6 is how much? It can schedule here or here, because this can stage down. So, probability here is 0.5, half 1 by 2. 7 is cannot schedule here, because 7 is already discussed that 3 and 7 is 0, right. So, and then probability of 8 is something, because it is 1 by 3, right, because this can schedule here, here and here, because 8 can come here also, right. So, because operation 9 can schedule here, so 8 can schedule here, here or here, right. So, there are 3 options. So, 1 by 3, which is basically 0.33. So, what I understood, so that operation type distribution of multiplier in timestamp 1 is 2.83, right. So, this basically gives you the concurrency, right, because this says that we need kind of at most 2.83 number of multiplier, which is kind of 3 multipliers in timestamp 1, right. So, it is roughly very abstract level. So, this we can actually calculate for each timestamp for each type of operation, right. So, for each time step for each operator type, right. So, I have to calculate this Q K L, because L will vary from 1 to n and K will vary for all type of 1 to K, right. So, this we can calculate, and we have the operation type distribution, and this is kind of giving me the kind of concurrency of that type of operator in a timestamp, okay, and that I have to do it for multiplier and adder, or adder is basically ALU here. So, I have to identify this, okay. So, let me take this complete this example, because we have already identified the probability of each operation in each timestamp. So, for example, if you take this operation V8, which can which time frame is 1 to 3, right. This is the ASAP time and this is ALAP time, hence it is basically 1 by 3, right. So, it can schedule in timestamp 1, 2 or 3, probability is 0.3 and V4 is 0. If you take V6, which time frame is 1 to, so the probability of operation 6 in timestamp 1 or timestamp 2 is 0.5, and operation 6 in timestamp 3 and 4 it is 0, right, because it cannot schedule in timestamp 3 and 4. And this I have already understood that P1 is 1 and P11 is 1 and P12, P3, P13, P4 is 0, because it cannot schedule in other timestamp, because it has a 0 mobility, it has to schedule in timestamp 1. Similarly, for P2. So, this way you can actually identify all the P value for each node in each timestamp, right. So, those is calculated, and then I have I told you that we can actually identify the QKL, which is the operator type distribution. So, it is just the summing of all the probability in each timestamp, right, and I already calculate this for multiplied in timestamp 1, which is basically 2.83. If you just do the same thing in timestamp 2, you will get 2.33, and it is, if you do it in timestamp 3. So, timestamp 3 is basically, it is I can calculate. So, for say in timestamp 3, so 3 cannot schedule here, only 7 can schedule here, right. So, which is basically in timestamp 3 7 can schedule. So, this is 0.0. So, basically P 7 in timestamp 3, which is 1 by 2, and 6 cannot schedule, 8 can schedule, because this 9 can schedule in timestamp 4. So, 8 can schedule. So, P 8 of timestamp 3 is 1 by 3. So, which is basically 0.5, 0.33, this is basically 0.83, right. So, this is basically, you can see this is 0.83. So, I can actually, and for 4 it is 0, because none of the multiplier can schedule in timestamp 4. Similarly, I can actually do the for addition, because say addition, this operation can schedule here, here or here. So, only this operation can schedule in timestamp 1. So, that is why it is basically 0.33, because P 10 of 1 is 0.33 and rest are 0, right, rest P I of 1 is 0, right. So, these are all for all operations are 0. So, that means this is Q 2 operator type 2 in timestamp 1 is 0.33. I hope you understand this, because this is just say the what are the operations can be possible to schedule in timestamp 1 of type k, right. So, this is 0.33 that we can understand. In timestamp 2 this operation can schedule, and this operation also can schedule, right. So, this is basically this is again 0.33, because it can schedule in any timestamp, and this is also 0.33, it is basically 0.66, that is what I got here, right. So, this way I can actually calculate the value for this QIK operator type distribution, this operation type distribution for each type of operation in timestamp k, and this is given by this. You can actually do at your you can try yourself also. Okay. So, basically what I have learned so far, that we can actually identify the operations type distribution, right, that we can actually identify the maximum kind of possibility of concurrency possible in each timestamp using the value that we have already calculated, right. So, now what is the analogy with the force, because we are actually try to develop a force directed scheduling in this class, right. So, now you remember that force was k into x, k was some elastic constant, is the displacement value. So, now in our context of scheduling, what is x, what is k, and what is f, let us try to understand that. So, basically as we have understood that because of the mobility, an operation has a probability, equal probability of executing in the time frame, right. For example, I have seen that V10 can schedule in 2, 3 or 4, sorry 1, 2 or 3. So, it has probability 0.33 in this all timestamp, equal probability. Now, let us suppose that you already schedule this operation in timestamp 1. So, earlier it was 0.33 in timestamp 1 and 0.33 in timestamp 2, 0.33 in timestamp 3. Now, you schedule it timestamp 1. So, what is going to happen? It probability become 1 in timestamp 1, probability becomes 0 in timestamp 2, probability become 3 in timestamp 0, probability becomes 0 in timestamp 3 also, right. So, that is the change in probability, right. So, that is what is the displacement in context of scheduling. So, it has equal probability in 3 timestamp, I schedule in a specific timestamp. So, probability will increase in that particular timestamp and probability becomes 0 in other timestamp, right. So, that is what is the elasticity here, right. So, the kind of displacement here. So, assignment of operation to a control state corresponding to changing the probability. So, probability become once where it get schedule and 0 for other places, right. So, change in probability is the displacement of the spring. So, this is my change in probability. Okay. Probability. Now, what is k? Because you already have calculated some this operator type distribution, right. So, that is something you already identified this QIL, QKL for each type. So, that means it is already because of the uniform distributions of the operations, according to their operation distribution, I have already calculated the type distribution, right, and which was saying that it was saying that in a timestamp what was the kind of concurrency you already can achieve, at max can achieve. Now, what is going to happen? Because you now move this operation here and there, so it will impact that value, right. So, here that this type distribution QKL is the my elastic constant, right. So, this is basically the type distribution QKL. So, that is the type distribution. So, I am going to multiply the change in probability with the this type distribution, because that is going to get impacted, and that is the constant value we have already obtained by distributing that operation in equal probably in all the timestamp where it can schedule, and then so basically that become my elastic constant in this equation, right. So, I am just trying to correlate the value that I have already calculated with this terminology. Okay. And what is the force? I have already talked to you that force is nothing but the concurrency. So, the force is, if you have a value high, that means a higher concurrency. So, for example, here it is 2.83, have a higher concurrency here, 0.83 here is a less concurrency, right. It is very obvious, right. So, so concurrency define the force, right. So, this is basically concurrency in our context, right. So, in scheduling constant, F is the concurrency, the number of operations can be parallelly executed in a timestamp, right. So, that is my F. K is the type distribution. Type distribution was basically, you understand, that is basically the kind of operations at max what is the kind of maximum concurrency can be achieved in a timestamp, and that is what we have calculated. And this X is the displacement in a mechanical context, and here it is the change in probability because of scheduling operation in a particular timestamp. Okay. So, this we have understood. Now, let us try to develop the algorithm. So, what I am going to do is that we are going to calculate the force for each operation, right, in each timestamp. We are going to calculate that force, and I am going to use that force as the priority function, right. So, if the force is high, that means it will actually increase the concurrency in a particular timestamp, and if the force is low, that means in a particular timestamp it will decrease the concurrency if I schedule that operation in timestamp, right. So, it is basically, you can actually think about the force of operation I, or say you can write this way, that force of operation I in timestamp L, because we are talking about whether I am going to schedule this operation Vi at timestamp L or not, right. So, I am going to, what I am going to do, if I decided to schedule this operation I in timestamp L, what is my total force, right. So, if the force is very high, that means it actually increase the concurrency in timestamp L if I schedule this operation Vi in timestamp L, and if the force is negative or less, that means it will decrease the concurrency in the timestamp, right. So, that is the kind of analogy or the priority function that I am going to consider, and using this priority I am going to schedule this, right. So, I am going to come to this actual algorithm latter part of this discussion. So, let us identify what is this force now, right. So far I have not talked about the force, we just calculate these things. I know that the force is concurrency, but how to calculate, right. So, how to calculate from this Qik and this Pi, whatever the value I have already obtained. So far, how can I calculate this force, right. Let us try to understand. So, there are two type of forces, one is basically the self force and another is the predecessor successor force. So, the self force is something, if we mention that, so self force, you can think about this operation Vi in timestamp L. So, you have this say this is your timestamp L, okay, and this operation I could have been scheduled here, here or here, any places. So, it has the, say the time frame was 3, right, the Ts, this is Ts I and this is TLI, okay. Now, if you schedule this operation here, and so you can understand, if I assume it is 3, so earlier the probability was 0.33, it was 0.33 here and 0.33 here, right. Now, you try to schedule this operation here, so here probability becomes 0, here probability become 1, here probability becomes 0, right? That is the idea. So, now if we just do this So, this is the change, basically the displacement, right. So, earlier it was 3.33, 0.33, 0.33, now it is 0, 1 and 0. So, this is the kind of displacement I can, if I think about the mechanical analogy, and then if we do this, what is the impact? That is given by the force, self force. And now, if you just schedule this operation here and there is a say successor operation of this node, now this successor operation, if I was decided to schedule this here, it cannot schedule here, right. But if I schedule this operation Vi here, the successor can schedule here as well, right. So, the impact, so once we actually calculate, decided the timestamp for operation I, it will impact the timestamp for the successor or predecessor node as well, because there may be some predecessor node also, that will also can now flexible, it can come here, right. So, that is something we have to calculate and which is given by the predecessor and successor force, right. So, let us try to understand how to calculate this self force and predecessor force. So, if you always recall that your force is basically k into x, x is the displacement and k is the elastic constant, okay. And we already know that this is my type distribution and this is the displacement now. So, let us try to find out this value now. So, now as I mentioned that I want to calculate the self force for operation Vi in time step L, right. So, basically the operations could have been scheduled anywhere between T to S, that I have already discussed, that it was basically the time frame. This is my time frame T I S and this is the time frame T I L, and this it can schedule anywhere, and I say try to schedule this operation in this is my time step L, okay. So, what is going to happen? So, I am going to because it could have been, so basically the probability of this operations was 1 by mu plus 1 in every time stamp where it could have been scheduled, right, and that was given by your PM, right. So, Pi of in time step L, PIL. So, now I am going to calculate this self force for all nodes, because these are the all time step it is going to impact it, as I shown in the previous slide, that if I schedule it here. So, it will become 0.33 to 1 and it is become 0.3 to 0. So, I have to calculate the force for all time stamp, right. That is why I am doing a summation from TIS to TIL, basically in this time frame range. What I am going to do? I am going to multiply this elasticity constant with the displacement. So, what I am going to do? This is my that QKM. It is the type distribution, operator type distribution in time step M of type K. I am assuming this the type of operation Vi is K, this is the operation type K, and I am going to multiply with the change in probability, right. So, here this delta Lm is called knocker delta function, which is can take value 0 or 1. So, it is basically you can understand that if this particular, so earlier the probability is equal in all time stamp, right, it is basically 1 by mu I plus 1, right. So, it is 1 by 3 or 1 by 2, 1 by 4, that we have understood. If there are range is 4, it is 1 by 4 and so on, right. So, earlier the probability was 1 by mu I plus 1, right. Now, if I schedule this operation in a particular time step n, then this will become 1. So, it will increase the probability. Earlier it was 1 by 3, now it has become 1. So, it is basically change in probability is 1 by 1 minus, it is the positive increment. So, 1 by mu I plus 1, right. So, then I am going to put 1 here, and for all other state where it does not schedule, it becomes 0. So, earlier it was 1 by mu I plus 1, it will decrease by this number, right. So, it is decreased by this number. So, I am going to put 0 here, so that this become minus 1 by mu plus 1, understood. So, you can understand clearly that this is the self force, because it was have a equal probability in this all time frame. I am calculating that if I try to schedule this operation in time step L, what is the overall impact? It will impact in all those time frames, concurrency in all those time frames. It will increase the concurrency in this time step and it is going to decrease the time concurrency in this time step. I am going to sum all this impact, right. So, whether it is impact positively here, it will impact negatively here, but I will take this summation of all this impact and then that summation is my self force, okay. I think it is understood. So, let me take the example and explain. So, say for example, this operation 6. So, operation 6 say it can schedule in time step 1 and 2, because you know that the time frame is 6 is time frame is 1 to 2, right. Operation V6 it can schedule in time step 1 or 2, okay. So, now let us, so I also know that this is a multiplier type operation, the type is multiplier and this is the q I, that q 1 of 1 is 2.83, right, this value, and this value is q 1 of 2 operator type 1 in time stem 2, which is 2.33, and you know that this P 1 6, sorry, this is in other way. So, that P 6 operation 1 in time stem 1 is 0.5 and P 6 2 is 0.5, it can schedule in this time stem. Okay. So, if I decide to schedule this operation in time stem 1, right. So, that means I am not scheduling it in time stem 2. So, what is my total cell force? So, that means cell force of operation 6 in time stem 1, which will be this q 1 1 into, because I have scheduling it here. So, I am going to put 1 here into 0.5 plus q 1 2, that means operator type 1 in time stem 2 into, this is 0 now because I am not going to schedule in time stem 2, minus 0.5. So, what I did, I just put this value into this equation, right. So, if I just do this and I can calculate, so it is basically 2.83 into 0.5 minus 2.33 into 0.5, and I will get some value, right. It will be a positive value, right. I think it will come, it is basically 0.5, yeah, 0.5 into 0.5. So, it is basically 0.25. Okay. So, this is a positive value. So, basically the conclusion is that if I, although this operation 6 could have been scheduled in time stem 1 or 2, what we will get is basically if I schedule it in time stem 1, it will increase the overall concurrency, because you understand that it will because it was already these two operations are scheduled here. If I put it here, so it will increase the concurrency in time stem 1, but overall concurrency will be increased. Okay. So, this is how I am going to calculate the cell force. Okay. So, this example was already here. So, I have already calculated. So, the value was 0.25, right. So, this is understood. And here, because if we schedule this operation in time stem 6, so it does not impact the scheduling of 7, because 7 could have been scheduled here or here, it does not impact it. So, there is no successor force here, because it will not impact the schedule of operation 7 or any predecessor or successor node. Okay. So, there is no successor force. So, now let us understand what is, now if you try to schedule the operation in time stem 2. Okay. So, if you try to schedule this operation in time stem 2, operation 6 in time stem 2, what will happen? So, this will come here and 7 will come here, right. So, this is 6 and this is 7. So, that means let us try to calculate the cell force first. So, change in priority in time stem 1 is negative, because earlier it was, so if I just write this cell force of operation 6 in time stem 2, which is basically 2.83, which is the q 11 into 0 minus 0.5, because it is not scheduled here, right. So, this is minus 0.5 and plus 2.33, here it is now scheduled. So, earlier it was 0.5. So, 1 minus 1 is, so if it is scheduled here, it will become 1, that knockout delta function minus 0.5. So, if you just do this, you will get minus 0.5. Okay. So, that is okay, that I do this. So, I will get minus 2.5. Okay. So, that something is understood, but you can understand now that if I schedule this operation 7 6 in time stem 2, now operation 7 is now impacted, right. So, now operation cannot be scheduled in time stem 2, because now, because this operation is dependent on 6 and it is going to execute here. So, earlier the operation in general, if the 7 has a possibility of scheduling in 2 time stem, now it is 1 time stem. So, it get impacted and it will create some successor force, right. So, now I will see how we can calculate the impact of 7 of scheduling operation 6 in time stem 2. Okay. So, how to calculate that, something let us try to understand. So, we have already understood that the cell force is minus 2.5 if I schedule this operation here. And what is the impact of 7? So, 7 now cannot schedule in timestamp 2, that is the bottom line, right. So, what we can do now is, so successor force is that, so this point 2.3 is the Q operation in timestamp 2, the type distribution of operator time in timestamp 2. So, now this 7 cannot schedule in timestamp 1, timestamp 2. So, that is why it is 0. Now, but it can schedule in time, it must schedule in timestamp 2, sorry, timestamp 3, right, because it is going to schedule here now. And the type distribution that Q13 is 0.8, that we have already calculated, right. So, this is the self force. If I just calculate this equation, you will get minus point so, right. So, that overall force is what? The self force plus successor force, which is minus 1, right. So, what we understood, if I calculate, I mean if I schedule this operation timestamp 6, then my total, so SF total force of operation 6 in timestamp 1 is 0.25, because it does not have any successor force, because it does not impact 7. But the total force, if I schedule the operation 2 in timestamp 2, it is minus 1, because it is minus 2.5 plus minus 0.75, it is minus 1. So, what does it mean? That if I schedule this operation in timestamp 1, my it will improve the concurrency, and if I schedule this operation in 2, it is reduce the concurrency, right. That is what we can understand from this total force, and that is what is the impact of certain operation to be scheduled in certain timestamp. Okay. So, let us now try to understand how we can actually calculate the successor force for all cases, right, because here you can understand that it is not, whenever you try to schedule a operation in a particular timestamp, it is going to impact all the successor and all the predecessor. So, I have to calculate that things for all successor and all predecessor, and I have to sum it up with the self force. Okay. And how I can calculate, let us try to understand. So, what I am going to do is this, the self force, we already know that self force is basically the summation from TIS to TIL, where I am going to multiply this type distribution with the change in probability, and the probability will be either 1 or 0 minus the actual probability. Okay. So, that I have already understood. So, what I can do, I can rewrite this equation as this. Let us see how. So, if I just do this, so it is basically summation of m equal to TIS to TIL QK m into delta LM minus summation of m TIS to TIL. So, I am going to multiply these two and these two. So, Q K M into PM PIM, right. So, what is going to happen? So, if we know that delta M is 1 for 1, where if it is for L, where it is actually getting scheduled, right, and for all other cases. So, I am actually talking about the timestamp L. So, delta L M is delta L M is sorry, this is delta I M, and delta I M is true for only this in timestamp L, right, and all cases it is 0, right. So, I can, if I just multiply this, so it is basically turn out to be that Q K L, because in L timestamp it will become 1 and other time it is 0. So, the summation will be 0. So, this is nothing but Q K L. Okay. So, that is what I got here, minus, and you know this PIM is 1 by mu I plus 1, because it is the probability in every time frame. So, if I just rewrite this term now, it is basically 1 by mu I plus 1, then summation into Q K M, right. So, that is what I got this equation. So, what I can do, I can rewrite my self force by this equation. Okay. Let us try to understand this. So, if you can understand here that this is basically the type distribution in timestamp L for type K minus probability into the type distribution in other timestamp. Okay. This is what the self force. Okay. So, now let us try to understand what is the predecessor or successor force. So, initially, as I mentioned, suppose I have this operation Vi can schedule here and here, and the successor node. So, there is a edge from this to this. So, this is my Vi and this is a Vj. and say this time frame of Vj is this Vi and time frame of Vj is this, right, because this is my for Vj, because if I schedule this operation here I can schedule it here, but if I schedule it here I cannot schedule it here, but I can schedule it here. So, this is the time frame. So, now if you schedule this operation Vi here, it is impacting here, it will not going to schedule it here. Now, the revised time frame become this, right. So, that is what is given by this. So, initially the time frame for a node is TIS to TIL, right. So, it was from TIS, this is say TIL and this is TIS, this is the range where it can schedule. Now, because I schedule the previous operation in some steps, probably I cannot say I can schedule it here say. Now, this is actually modified to this, right. This is my TIL tilde and this is my TIS tilde. And similarly, it can get impacted if there is a successor node is impacted. So, this TL can also get impacted, right. So, what is going to calculate is that the self force, that predecessor or success force is that what was the actual self force when the range was TS to TL and what is the range when I actually it terminated to TIS tilde to TIL bar, right. So, this is the my revised frame. So, if I just subtract this revised one, right. So, or say change in basically this minus this, right. So, if I just revise this, so earlier it was this value, it was this value and now this is value, this is change is this, right. So, this minus this. So, if I just put this in this equation TIL and TIS and then next time you put TIL bar and TIL bar. So, then if you do a minus, this two term will be, so I will just write down here. So, this is my for TIL, okay, and minus QKL, and so this will become plus now because there is a bracket here. So, this will become mu I plus 1 and then this is 1 by mu plus 1, sorry, 1 by mu I plus 1. So, here now the mu also change, right, this will become mu bar and then this become m equal to T IS tilde to TIL tilde, because this is the revised one. If I just do this, what is going to happen? This and this will be calculated, separated out. So, this minus this. So, this is what I got here, right. So, so basically once I schedule a operation in say its some node in time step L, it will impact the time frame of the successor node as well as the predecessor node. So, for all successor or predecessor, what I am going to do, I will calculate the self force when it was could have been done in any time stamp and it is in the revised time frame, right. So, this is the revised time frame, the tilde, and their difference is the predecessor or successor force, right. So, basically I am now impacting the overall schedulability of the predecessor node. Similarly, I can also do the for successor node. Okay. So, this I can calculate. So, let me just give an example. So, suppose I schedule this V8 in time stamp 2. So, you understand that V8 time frame was 1, 2, 3, right. So, 1, 2, 3 and V9 was the time frame is 1, 2 to 4, right, because it can schedule in time stamp 2, 3 and 4. Since I schedule this V8 in time stamp 2, now V9 can only schedule from 3 to 4. So, its revised time frame become, so it was earlier 2 to 4, now it become 3 to 4. What I can do? I can just find out what is the self force once it is 2 to 4 and what is the force when a self force when I calculate it is basically 3 to 4 and I can make the separate out the difference and that is the change in force, right. So, that is what I am done. So, for V9, so this is the revised force 1 by 2 because it is now it can only schedule in 3 or 4. So, there is a probability is 1 by 2 into Q23 because it is on time stamp 3 or 4 of type 2 because this is a operator type plus, right, this is operator type plus and it is Q24 3 or 4 and earlier it could have been scheduled in 2, 3 or 4. So, it is q 2 2 q 2 3 and q 2 3 4 1 by that. Okay. So, if I just do this I will get 0.3. So, what does it mean? So, that if I schedule this operation 8 in timestamp 2, that predecessor force due to this schedule is 0.3, because this is can only impact this node. If it is so, if I now think about this node, right. So, it will impact this node and this node. So, you have to calculate the this predecessor or successor force for this node as well as this node, and then you have to sum it up with the self force for this 7. Okay. I hope you understand this. So, what I have to do it? I have to do it for whenever I schedule a operation Vi in timestamp L, Vi in timestamp L, it will impact. So, suppose this is impacted. So, there are say there may be 2 3 predecessors of this node, and there may be 2 3 successors, right. So, I have to calculate this force, that predecessor or successor force for all these 6 nodes, right, all the nodes that are going to be impacted by the schedule of this node, and I have to add that particular force with the self force of this node, and then only I can actually identify the total force. And if the total force is high, that means it will, if I schedule this operation Vi in timestamp L, it will increase the concurrency, and if it is low, that means it will decrease the concurrency. Okay. I think it is clear to you now, and now I will talk about the little bit of complexity issues here. So, what is the overall complexity? So, what is the calculation of the distribution graph? So, distribution graph is this, right. So, for each node, what is the value for this? So, this can be calculated. So, you have to identify the probability of each node I in each timestamp, right. So, it is basically of order of n, if I assume there are n nodes, n into L, right. And since this L is basically is a time frame which is very fixed, I can actually assume this is order of n, and then I have to sum it up, right. So, I have to just sum it up this for each type k and each timestamp L. So, this is basically the calculus of the distribution graph will be order of n. And what about the self force? Self force is order of n because it does not impacted the other predecessor or successor node. So, if I just I have to just how do I calculate it? For all the time frame, I have to just multiply the type distribution with the probability, that is all, right. So, this will be order of n because it you have to calculate for each node, okay, for each node for its time frame, and time frame is a very fixed constant value. But this predecessor or successor for node is order of n square, because this is has to done for all node, right. So, for each node, for each successor or predecessor node, right. So, this is order of n, this is order of n, because whenever I take a node, I have to check how many nodes are the predecessor and how many nodes are successor, and for each of them I have to calculate this. So, for every node I have to search the whole graph again to identify the predecessor and successor node, and then you have to calculate their force. So, it will be basically order of n square. Okay. So, this is the high level, no need to think too much about this, but this is bit basically complex to calculate this. Okay. So far we have so now if you just to recap, we have understood what is the force, right, and what is the how it is going to calculate it. So, in conclusion, we have understood what is force and how to calculate force for each node, and in summary the force is basically is the kind of concurrency for it is a concurrency of the operations when I am going to schedule a operation Vi in a particular timestamp, and how it is going to impact the concurrency in the subsequent nodes, right. So, that is something we have calculated, and in the next class I am going to see how I can utilize this force in developing the scheduling algorithm, both MLRC and MRLC. Okay. Thank you.